Here we have another example of two objects that are connected, so they will be moving together. We're told this system is released from rest and it moves 50 centimeters in 1 second. Now we do need to make an educated guess as to the direction of motion. In terms of the block on the incline, it does not have a pulling force that could make it speed up to the left. Now there's going to be friction opposing the motion, but if this block is released from rest, it's going to be the tension in this cable that gets this block speeding up and accelerating. So that block will accelerate to the right, while the hanging mass will accelerate downwards. We are assuming massless, frictionless pulleys in all of our problems right now, which means the tension everywhere in that string connecting the blocks, that tension will be the same. All right, so it's telling us it moves 50 centimeters in 1 second. That means the block down here is also moving 50 centimeters in 1 second. Knowing it starts at rest, either one of them starts at rest, moves a distance of 50 centimeters in a time of 1 second, this is going to allow us to calculate a value for the acceleration. So going back to our kinematic equations, the one that deals with position and time, delta S, if I bring S initial over, S final minus S initial is our delta S, so we know that. Our initial speed is 0. It tells us the system is released from rest. So this delta S will equal 1/2 HE squared. We know the time, we know the distance, so we're able to calculate the acceleration here. So what, 1 meter per second squared. This acceleration is going to be the same for both the block on the incline and, sorry, not the incline, the surface, and then the hanging. But when we say that, we mean the magnitude of the acceleration. The numerical value is the same. Both of them will accelerate at a rate of 1 meters per second. I hope it's obvious that the directions of those acceleration are different. But that's okay. To account for those directions, we need to look at the objects, these masses, individually. I'm going to call the 3 kilogram mass on the table M1. Just as we've approached problems up until this point, we're going to draw a free body diagram. So we know the mass on the table is experiencing tension to the right, a normal force up, force of gravity down, and then some kinetic friction to the left. I know that because they've given us a coefficient of kinetic friction. You hopefully remember or can look up that the force of kinetic friction is equal to the coefficient times the normal force. So to relate these forces to the acceleration this block experiences, we need to use Newton's second law. The net force in the x direction is going to equal the mass of this box, so M1, times its acceleration in the x direction specifically. So we know tension is to the right, We know the force of friction is to the left. Those are the only forces in the x direction. So that sum of force needs to equal the mass times the acceleration. In the y direction, the normal force upwards needs to balance out the force of gravity downwards, because while this block slides on the table, it will not have an vertical acceleration. It will not be accelerating up or down. So what I'm going to do at this point is in place of the force of friction, I'm going to substitute in the coefficient times the normal force. So just wanting to pull these things together and see where we're at. We know this coefficient of kinetic friction. We know the mass of this block. We know G. We know the value of the acceleration. We found that using the kinematic equation, the big three. So we actually, in this case, have enough information to solve for the force of tension. The coefficient of friction they gave us is 0.18. The mass is 30 kilograms. And we calculated the acceleration to be 1 meter per second squared. We do know the acceleration is pointing to the right, which is why I'm just putting the value of 1 in there, as opposed to a -1. So plugging this in, I'm finding this tension to be 532.2 newtons. Which, interestingly, that is the answer to part B. So we've answered part B already. Now, in terms of significant figures, I would say it's about 530 newtons for part B. Because we only have, at best, 2 sig figs here. The other part, we want to know the value of m, where m is the mass of the block that is hanging. Well, we need to be able to look and relate the forces on that block to its acceleration in order to get m into the equation. So here's our mass. This represents the hanging mass, so it is experiencing the force of tension upwards, a force of gravity downwards, and remember, we've said that its acceleration is downwards. I'm just writing that over to the side. I don't put it on the free body diagram because in and of itself, that is not a force. But when we write out net force equals ma, we have to account for the direction. So here we know there's a tension force up, force of gravity down. So that represents the net force. This will equal the mass of this block times its acceleration. But again, I need this negative sign in here to represent that it is accelerating downwards. So we've calculated the tension. We're looking for the mass. I put in -1 for the acceleration. We now have m in 2 terms, so we will bring the m term to the other side, and we can solve for this mass. Let's see, 2 sig figs, so we have 60 kilograms would be this mass. That seems rather large. Let me double check my calculations. Okay, coming back here, I think my issue is right here. So 0.18 times 3 times 9.8 plus 3, so I apologize. The tension ends up being 8.3 newtons. That seems more reasonable. I am going to use the more digits in terms of solving for the mass. That seems much better. When the block on the table is only 3, I would assume to get a relatively small acceleration, the hanging mass wouldn't be particularly large. 60 kilograms was a whole heck of a lot bigger than 3. I would expect that motion to happen a lot faster. So I apologize. Incorrect number there. So tension ends up being 8.3 newtons. The mass ends up being 0.94 kilograms.